Welcome back, and this is the next in the series of videos looking at the transition metals. And in this video we're going to look at two very important reactions, deprotonation and ligand exchange, and you're going to need to learn these for all the different transition metals. So you're going to need your notes, and we're starting on page 15. So the first reaction we're going to look at is deprotonation, which does exactly what you think it does. It removes a proton, a hydrogen ion, from the transition metal complex. How much deprotonation occurs depends upon the strength of the base. So water, which is a very weak base, that can only deprotonate 3+ ions. So the example we're going to use is the iron 3 ion. So if we draw out the full thing, we have our iron 3+ ion with its 6 water ligands. Now, because the iron 3+ is very small and very highly charged, it's quite polarizing. So it's able to distort the electron cloud around the water molecules. So just putting the last few in. Notice again, I'm showing that it's the oxygen that's forming the dative covalent bond with the iron. If I take a water molecule outside of this, remember the water molecule can act as a base, it can accept a proton. Because this bond here between the oxygen and the iron has become distorted, it's weakening the bonds within the water molecule, pulling the electrons through towards the iron. So basically that means that this oxygen can grab that hydrogen, pushing the electrons back on to that oxygen. And we get a complex ion now with only 5 waters and 1 OH group. So we've removed one of the hydrogens from this water molecule, and it's now become an OH group. So now this whole thing has an overall charge, because you've still got the 3+ ion here, but you've got the 1- here. This overall complex now has a 2+ charge rather than a 3+ charge. And you can see that here. We've got 5 waters, 1 OH group, and your Fe group here, which is 3+. So overall, this is 2+. And this is why solutions of iron 3 compounds are often acidic, because you've got the excess hydrogen ions. Now, this doesn't work with iron 2 because the iron 2+ ions are not polarizing enough. So those ligand bonds will not be polarized, and therefore the hydrogen delta positive is less likely to be attracted to the lone pair of electrons on the water molecule. However, if you have a stronger base, such as the hydroxide or ammonia ions, then you can remove more of the hydrogen ions. You can do that until you get to a solid. In other words, once this is neutral, it will drop out of solution. So as long as you've deprotonated enough times to make a neutral complex, that complex will then drop out of solution as a solid. Now, this is slightly complicated by the fact that some of the hydroxides of the transition metals are amphoteric. Amphoteric means, remember, that they can act as an acid or a base. So chromium 3 hydroxide can act as both an acid or a base. Here it's acting as an acid because it's releasing a proton to the OH negative ions. So we'll look at this reaction in more detail, but it goes from a solid precipitate to a solution when you add excess hydroxide ions. So the second reaction we're looking at is ligand exchange. And again, this does exactly what you think it does. It is where one ligand is replaced by a different ligand. So ligands have different strengths. So some are stronger ligands than others, some bind more effectively. So for example, cyanide is a stronger ligand than water. So the cyanide will bond in place of the water and kick out all of the water molecules. The second example of these are where some of the ligands are replaced. So a good example of this is the copper when it reacts with ammonia. Initially, it forms a precipitate of copper 2 hydroxide, but then if we add excess ammonia, we move on to a ligand exchange reaction where 4 of the ligands are replaced with ammonia ligands, and we get a tetraamine diaqua copper ion. Notice the amine ligands are around the centre, with the 2 water ligands above and below the plane of the molecule. This is what we call a distorted octet. What you will see happening is this. So when we add a small amount of ammonia to a solution of copper sulfate or copper in some sort of solution, we get deprotonation. That forms a precipitate of copper 2 hydroxide. So that's where 2 of the water ligands have lost a hydrogen ion to become OH negatives. It is now neutral, and that's why it drops out of solution. So the formula there would be Cu. It's still got 4 water ligands, but it's now also got 2 of the water ligands have become OH negative ligands. Now, because that is neutral, that is why, remember, it is a solid. But if you add excess ammonia, some of those ligands, the 2 OH negative ligands and 2 of the water ligands, are replaced by ammonia ligands, and you get this colour change to this dark blue solution. So it's a classic test for, have I got copper 2+ ion present? Does it do this reaction with ammonia? The last type of reactions that transition metals typically undergo is oxidation and reduction. And you know this from our work at lower sixth. Transition metals are usually either very easily oxidized or very easily reduced, and they make good oxidizing or reducing agents. Think about zinc being a very good reducing agent, and manganate and dichromate being very good oxidizing agents. They readily change their oxidation number, and that's why they can act as oxidizing and reducing agents. You do need to be aware of all of these and the observations. So these are good oxidizing agents. You should be aware of all of these equations and the observations. So things like the purple manganate decolorizing, becoming Mn2+, or the orange dichromate going to the green chromium 3+. Sometimes you will see that one going blue because you formed chromium 2+. You managed to force the oxidation number down even further. Good reducing agents, on the other hand, can be things like zinc, iodide, or Fe2+ ions. All substances which are very easily oxidized, so they're very good at losing electrons and therefore acting as reducing agents. So that just goes over the main reactions of the transition metals. That's deprotonation, ligand exchange, oxidation, and reduction. And in the next section of the notes, you're going to be doing lots of different practicals which will look at colour changes and being able to relate those colour changes to the equations. So until later, take care, stay safe, bye-bye.